I think we should start now because
Okay.
whoever is joining late, they will have to just they can go through YouTube video and they can just pick up from there, and we should start. So we welcome Dr. Ragothama in the second on the second day of this web series, which is based on NMR. So yesterday, sir told us many things about NMR, and we could learn the basics of NMR, that what this NMR is and how the technique was developed and how helpful it is for not only for chemistry, but for the material sciences and other sciences too. So we welcome you, sir, again, and I'd like to request students to please, however, the video is available on YouTube also. You can just anytime visit YouTube link, and you can rewind it, and you can just try to learn as much as you can. But still, I request you to take notes of what Dr. Ragothama is telling us. And here I have announcement for students. I am announcing it today because tomorrow you will say that I have announced late. So there will be an assignment which will be submitted by you. I will be hosting that assignment on the 7th, and that assignment will be based on the lectures of Dr. Ragothama. And then I request sir to please send us the 5 to 6 questions also based upon his lectures, so that we can just see that how much students have learned. This will be a graded assignment, and it will have 25% weightage in your CC examination, that is comprehensive cumulative evaluation. It will have 25% weightage. So with that purview in your mind, you keep this in mind, and please take notes so that you can just attempt the assignment, and you can fairly do in that assignment. So I request Dr. Ragothama to please go ahead with his slides. Thank you, sir. Floor is all yours.
Okay. Okay, good, good morning, everyone. So we will continue from where we stopped yesterday. Now, yesterday I introduced you about the basics of NMR and how currently the pulse NMR we are using, and what are the difficulties. The main problem with the NMR is the sensitivity. There are so many developments happening mainly to concentrate on the sensitivity enhancement. And now to get the information, there are so many pulse sequences now, or so many dimensionalities. So what I'll be covering is mainly the 1D part of today, and probably I'll cover 2D part also. And towards the end of today, probably I'll introduce you to some basic 2D principles, and then continue tomorrow and try to give some examples. Because I work on peptides, it's easy for me to explain these 2D principles in a peptide. So continuing further from yesterday where we left, yesterday I showed you, I stopped at this slide, which shows as the size increases, the complexity of the spectrum increases. And this is an octopeptide. It's already so complicated. As I said, it is a full spectrum. I simply cut it at places and put one above the other. So normally the whole range is about 0 to 10 ppm. So what is this ppm? What is this chemical shift and all? I'm going to cover it today. Now, because of this complexity, so we need to go to the higher dimensions to remove the complexity and to get more information. That is where our 2D comes in. Now, this 2D plasma has two axes, both a frequency axis. And on the diagonal, you see this 1D spectrum. And now this is the 2D normally represented as a contour plot. It's nothing but this is 1D stacked plot. I forgot to get that picture. Probably tomorrow, if I get it, I'll show you that picture. One can look at the stacked plot, stacked one above the other, about 256, 500 plots and all. But it's difficult to visualize. So what they do is look from the top, take different cross sections, and draw it as a contour plot, exactly like mountains are represented by these contours. Now the peaks are considered contours. You chop off at different levels and get these contours. So that's how it's represented. And now it improves what do you say? It spreads the information in 2 dimensions. So a little clarity is obtained. At the same time, a lot more information is obtained We will see all those things as we go along. Now, for today, I'll continue with the 1D NMR. And now, having recorded the 1D NMR spectrum, what are the information we are going to get? So we see one by one what are the information we get from this NMR. Now, this is a typical 1D standard textbook, very first spectrum of ethyl alcohol. And what are the parameters we get from them? There are 4 or 5 important parameters. It could be many more, but we will restrict to 4 or 5. The most important parameter here is the chemical shift. Now, what is chemical shift? It simply represents the position in the NMR spectrum. Where does it come? And normally, it's all the time is a relative position, relative to some standard used in. So normally, I'm sure you're all studied in the basics NMR. The standard would be what is known as the TMS, or tetramethylserine is used as the standard. So we will see that why we use TMS and all as we go along. And it's simply with respect to TMS at what position it comes. So different groups, depending on the electron environment, gives at different positions. So this is a very important, most useful parameter in NMR. And any small perturbation, it's unique to a molecule. Any small perturbations is reflected on the chemical shift. So even structures today, though there are so elaborate, involved experimentation to be done to obtain structures, because now there are so many structures available, and due to the softwares and developments in NMR, people want to simply look at the spectrum, look at the chemical shift, and get the structure information directly from the chemical shift. So it's such an important parameter. So we will go more detail as we go along. Now, the second important parameter is what is known as the spin-spin coupling, or the scalar coupling, represented by J. Now, when you look at the spectrum, most of the proton or even carbon-13 in a spectrum, so let us restrict ourselves to proton spectrum, it won't be a single line, so like this atomic spectrum. So there will be, it could be a singlet, it could be a doublet, it could be a triplet, it could be a quadruplet, it could be a multiplet. There will be splittings in each lines. Now, this is caused because it interacts with the neighboring spin, which is covalently linked. So the covalent link is very important here. Only if it is covalently linked, it gives rise to this kind of splitting. Now, this also has very good information when you talk of structures. Now, all protein structures are defined by the dihedral angles called phi and psi. Now, one of the these phi and psi are correlated to the spin-spin coupling constant, especially the phi is straight away one can get from measuring these coupling constants. So we will again see as we go along more about this spin-spin coupling. Now, the next is the relaxation parameter. This is again yet another important parameter. But at the moment, for today's lecture, we won't dwell too much on it, but I'll introduce you to that. But that's from physics point of view, is a very important parameter from the dynamics point of view. If you want to study of protein dynamics, how protein-protein interact, how protein-ligand interact, so these relaxation parameters are very useful there. And this is one of the reasons why we cannot go to higher molecular structure determinations, macromolecular structure determination, because as the size increases, the relaxation rate increases. It results in the line width increase. So there won't be any sharp line. They will all be broadened, and the features in the NMR spectra is lost. So that's another reason. So there are, again, under relaxation, there are 2 kinds of relaxation called longitudinal relaxation, represented as T1, which kind of represent the intensity of the signal. And the second is the line width of each signal. So which is related to what is known as T2 relaxation, which affects the line width of these resonances. And the most important parameter from the structure point of view is what is known as NOE. NOE stands for nuclear Oberhauser enhancement. And this is unlike J coupling, which goes through bond. This goes through space. You don't have to have a covalent linkage. And if any two nuclei come close by within 5 angstrom distance, they interact with each other and they exchange magnetization and results in signaling. If you irradiate one particular signal, the effect is seen on the other signal, either an increase in the signal intensity or decrease in the signal intensity. So now this change in the signal intensity is a measure of distance, because that has a relation of 1/r⁶ is a very sensitive parameter. Again, one can estimate distances now in a protein structures and all, because it has the linear amino acid chain fold into globular structures, and some fifth residue can come in contact with the 200th residue because it twists and turns, and then maybe if they come close within 5 angstrom distance, they can interact, and you can estimate the distances. And if you see more and more NOE, in a typical protein spectrum, we see hundreds of NOEs. The more the number of NOEs you get, the better would be the structure. So how these NOE are obtained and all, we will go one by one parameter. So these are the 5 important parameters we get from the NMR. And now I'll go on describing one by one. Now, the first one is the chemical shift. Now, chemical shift is represented by the Greek numerical delta. So delta, or the chemical shift, is the main pillar of chemical applications. It's kind of fingerprint of the chemical structure. Each molecule has a unique NMR spectrum. So no two molecules have the same NMR spectrum. It's a unique given molecule. So then that way, any small changes, there should be some other thing interacting or something else happening. So this is that way is a very unique parameter associated with a particular molecule. Now, how does it arise? It arises because now, as I said, we are looking at the protons inside. All the time we are considering only the hydrogen atom. Hydrogen atom has a proton in the nucleus. Now, there is no bare nucleus. Now, when you put it in, as I said, the NMR all the time needs external magnet, because these spins has to align to energy levels, and then you have to provide energy to make the transitions. Now, when you put this molecule, any molecule in the external magnetic field, there is no bare nucleus, they're always surrounded by electrons. So the nucleus, the protons inside the nucleus doesn't see the external field, but what it sees is reduced external field. So in the sense, it's kind of shielded. It's not exposed to the whole external field. There is a small reduction. And there is only a very small reduction influenced by the surrounding electron. Depending on the kind of electron surrounding the nucleus, whether it is water molecule, the alcohol molecules, the methanol molecule, acetone molecule, whatever it is, the surrounding electron influences the amount of field seen by this protons inside the nucleus, and this how much its shield is given by the shielding factor. Now, what the nucleus sees is not the main magnetic field B0, but some reduced version of it given by sigma B0. So what it sees, the B nucleus, the magnetic field of the nucleus is B minus sigma B0, or you can call it B0 1 minus sigma. Now the sigma decides where it should come with respect to TMS. So if there are different kinds of proton, like in ethyl alcohol, there is a CH3, CH2OH. All these three kind of proton has different environment, and they get exposed to different magnetic fields, and that's how you see they are resonating at different positions. Now, chemical shift doesn't exist in the absence of external magnetic. There is no external magnetic field. They all collapse into one small range. Okay. Going further, as I said, the shielding depends on the chemical environment, what is exposed to. Now, each nucleus results in a unique local magnetic field. So it's called the B local. What it sees is not the main magnetic field, but a local magnetic field. So essentially, B effective is B naught minus B local. Now, as I said, this local field is very small compared to B naught. B naught is very much larger than the B local. When we talk in frequency units, is megahertz versus hertz. Now, when we talk of this chemical shift, we should be talking, if you record the spectrum in a 500 megahertz spectrum, we should be talking of 100 million, 20,462 is one P, 500 million, 20,622 is another P. So this gets cumbersome. So because this million is common to everything, and the whole spectrum range is only in a few thousand hertz, we can remove this million part. And now for that, we need a reference compound. That's where we need a reference compound. Now, with respect to that, if you measure, it would be only in hertz range, which is easy to do. So that is why a reference compound is used. A relative scale, only the difference, a small number of measured is useful where the megahertz is separated. Because all are in megahertz, you can take out the megahertz as common factor and simply express in unit of hertz. Hence the use of reference material like TMS, which is set at 0. So it's because you set it at 0, it's easy to refer with that. You can set it to any value. It need not be TMS. One can set it to water. Normally comes at 4.5 with respect to TMS, or you can reference, make water 0 and tell with respect to that. Or you can make acetone 0, tell with respect to that. But the noted convention is they use this TMS because it comes at the one extreme position, and that is set to 0. And with respect to TMS, everything else is measured in organic solvents. But then when it comes to aqueous solutions or some other solvent where TMS may not mix with that, so we use some other reference, like in water samples, we use what is known as TSP. We will come to that probably in the next slide. Now, before that, now the measurement of the chemical shift, the x-axis in the NMR spectrum is always the frequency unit. Now, this frequency unit is a disadvantage because there is now there are hundreds of spectrometers, or in all over the world there are thousands of spectrometers. Each one has his own spectrometer. It could be 400 megahertz, it could be 800 megahertz, it could be 1000 megahertz, it could be 100 megahertz, and various things. Now, this frequency is dependent on the magnetic field. So each one, when they say the chemical shift, they say what is the magnetic field used, and becomes again cumbersome. So what people did was to remove this frequency unit and convert into what is known as a delta unit or a ppm scale. You simply take the ratio of the frequency difference versus the spectrometer frequency, which remains constant irrespective of the magnet. It can be 400 or 500, 600, 800. If you take this ratio and express in the ppm scale, it becomes a standard everywhere. So this is the same number in whatever spectrometer you read. Now, how do you define this ppm scale or the delta scale? It's simply the frequency of the measured resonance. I call it frequency of the sample, measured the frequency of the reference, which is set to 0. If you set to 0, it's simply the sample. And now this megahertz is taken out. And if you divide by the corresponding spectrometer frequency, it turns out to be hertz over megahertz, which is parts per million. Megahertz is a million hertz. So this is a part in a million. So that is why it's called ppm scale, parts per million scale. So this is generally used. And again, is the convention to use this scale. And wherever you see NMR spectrum, you see this delta scale or the ppm scale. Now, finally, how do you define a chemical shift? Chemical shift is the difference between the position of a signal of interest to that of a reference. It is relative term. It's not in absolute term. It's always related to some particular reference. And normally it would be the TMS and expressed in dimensional units called the ppm. Okay. Now, as I said, there are again in the beginning debates which is the best reference compound and all. And eventually it was decided one to use a TMS. Why TMS? Because it's quite inert material, does not react with your substance. Highly shielded protons. There are 12 protons that all resonate on one particular position. So we will see that as we go along. And now they are all attached to silicon, and it shields this magnetic field quite strongly, and then it comes at one extreme right side of the proton spectrum. So that way it is good to use this as reference. And because of this 12 proton, the intensity shoots up and you use very tiny quantity. Not a few 5 to 10 microliter would be sufficient per sample. And it has low boiling point. It boils around 45, 50 degrees centigrade, I think. So you can easily remove that also. So that way, this is a standard used. But the problem is the TMS doesn't mix well, it's not miscible with water. So in case of water, we use another substance called TSP or the DSS. TSP stands for trimethylsilyl-propionic acid, and it comes as the sodium salt. Now, there are so many different kinds of proton here, but we are interested only in this tertiary methyl group. So because to avoid the other CH2s, we deuterate them. And this gives only one signal from this. And again, it comes at the highest field. And one can reference it to 0. You can set this 0 in case of water molecules and then water solvent. And with respect to that, you can quote the chemical shells. Okay. Now here is an example explaining the same thing. Now they are all expressed in frequency units, but as I said, the absolute frequency is difficult because it depends on the magnetic field. So different magnetic fields will have different frequencies. Hence, for the same sample, the reading would be different in different spectrometers. Now, what I've done is simply a cartoon diagram of different streaks of solvents where it comes in a particular spectrometer. Now, this is recorded in a 300 spectrometers, which has a 7 Tesla magnet. And now TMS, wherever it comes, it's set to 0. Now you have an option on the spectrometer. You can set any, whatever signal you want to 0. And now once you set to 0, the rest are all measured with respect to that. Now, if you express in frequency unit, normally NMR spectra are in frequency unit, but for our convenience, we convert into ppm units. Now, the acetone, this case comes at around 600 hertz, whereas water comes at about 14 or 1500 hertz. Methanol comes at around 2300 hertz and all. But the same thing, when taken in a 600 spectrometer, the frequency changes. The position remains same, but because the magnetic field is doubled, the frequency is also doubled. Now, instead of coming at 600, acetone now comes at 1200. Water comes at around 2600, whereas methanol comes at about, whatever it is, 4000 something. Now, this is cumbersome. Again, every time you have to tell which spectrometer you recorded and all. So what they do is you simply take this hertz, divide by the spectrometer frequency. In this case, 600 by 300, or in this case, 1200 by 300. If you do that, you get the ppm scale. So 600 by 300 is 2, 1200 by 600 is 2. So also the chloroform is normally it comes at 7.2, whether you divide this hertz by 300 or 4,600 or 800 by 600 would be 7.2. So whatever spectrometer, if you express in ppm units, this number remains same. So henceforth, we will all stick to this number in the ppm scale, which is independent of the spectrometer. Before that, I just want to tell you that the historic facts are important. Now, when 1950s, 60s, when they discovered this, they used what is known as a tau scale. Now, because the TMS comes at the one extreme, the highly shielded proton, they said they should give a highest number. And now the proton spectrum comes in the 10 ppm range, they said put TMS at 10 ppm, and the rest are all below that because this is the most shielded. But later on, it found out that there's aldehydes, ketones, and all come below zero. So the -1, -2, and all becomes difficult. So now then people said, why take it at zero? Take it at 10, take it at zero, and they called it the delta scale. Now the relation between tau and delta is tau is equal to 10 minus delta, or delta is equal to 10 minus tau. So, but currently we use delta scale where TMS is set to zero. Now, this was the problem in 50s and 60s, year 1950, 1960s, people were changing over, and in these exams, they used to give they have to ask some questions, and they mention the chemical shift. They mentioned the chemical shift in tau, but some of the students are used to this delta scale, so they used to give delta as well. And then ask questions, what happens when this is a water proton, what would be, if this is the NMR spectrum, what would be the molecule and all. So now later on, this is no more a trouble now, but simply for historic sakes, I'm telling you, there was a delta scale. If someone goes back and refers to 1950s paper, you see this delta scale. One need not be confused about that. But currently, this is obsolete. We never use delta scale now. We all the time use, tau scale, we all the time use delta scale or the ppm scale. Okay. Now, there is, when you read your literature, one has to be familiar with these notations. And now this is the delta scale. Again, I have used the same solvent NMR spectrum. And now every peak here, and this notation is, instead of seeing these numbers, if they want to refer any two things like acetone, because TMS is highly shielded, acetone is kind of de-shielded with respect to TMS. So we say when you refer acetone, we say it is de-shielded with respect to TMS, or water is de-shielded with respect to TMS. Water is also de-shielded with respect to acetone. It's simply the left side is called the de-shielding or the downfield. Anything below TMS, all these nuclei are called downfield when you refer to TMS. Now, when you look at water, it is downfield of TMS, but upfield of chloroform. So with chloroform, it's on the right side, but with respect to TMS, it's on the left side. So now one should get used to these kind of vocabulary when you refer in papers. They simply say certain proton is downfield of certain other proton. When you say downfield, it is left side of that. If it is high field, it is right side of that. So they use the word low field or downfield or high field or upfield. Now they say it's de-shielded or it's more shielded. And again, if you express in frequency unit, sometimes that is also used. On the left side, these are all high frequency. On the up side, it's all low frequency. And even refers to the paramagnetic effects. The paramagnetic always de-shields this thing. So anything on the left is called paramagnetic effect, or anything on the right is called diamagnetic effect. So one has to get used to this notation in case you read your literature. Instead of numbers, one can say, as I said, the water molecule is upfield of chloroform. When you say DMS, it's downfield of acetone or TMS. So such vocabulary one has to get used to. Okay. Now, as I said, it's a very sensitive parameter. A lot of things which influence this chemical shift. The main thing is the electronic shielding, electronegativity of the atoms. If there is a fluorine substitution, it gets further down shielded compared to chlorine and all. Aromatic ring currents also affects us. I don't have time to go into all these details. Maybe some other time you see. So aromatics plays an important role in protein structure. There are aromatic ring current shifts. So there's a normal spectrum, but there is an aromatic ring, they will have special effect. Suddenly you see certain things moving drastically. Now this aromatic can move upfield and downfield. Both are possible. And I don't have a slide at the moment to show you this. But anyway, the chemical shields are affected by these aromatic ring current effects. Now, hydrogen bond, again, very useful, very important parameters in protein structures, is also influence the chemical shift. Normally, when things hydrogen bond, it is the electronegative atoms like oxygen or nitrogen gets hydrogen bonded to another NH proton. Normally in proteins, the carbonyl oxygen gets hydrogen bonded to the amide hydrogen. So because of this, because of the hydrogen atom is electronegative atom, that whichever it is hydrogen bonding to, it gets shifted. So you see a signature of that in the chemical shift, then you can say that particular proton is hydrogen bonded. And paramagnetic effects, if there is a paramagnetic, like metal or something binds, you see drastic change in the chemical shift. And finally, even as I said, the structure has influence, like secondary structures, or helical structure or beta sheet structures have some influence. I have one slide showing you how simply looking at the chemical shift, one can estimate the secondary structures. Now this is becoming the normal. Now, as I said, NOE is the most useful parameter to get these structures, but because so many structures stored in the data bank, and now they analyze that and then they convert into the chemical shift, and then from that they deduce that the empirical relations. Now, if a particular piece comes at a particular position, it can be a helical structure, it can be a beta sheet structure. So structures also influence this chemical shift. So there are various things which affects the chemical shift. Now, with that brief exposure to chemical shift, let us move on to the next parameter. Now before moving to the next parameter, here is a typical values of chemical shift of various compounds. Now, this could be useful, again, textbook material. Now, here is our famous TMS. We have the methyls or any aliphatic proton coming around to 1 to 2 ppm. Alcohols and other things come around here. Olefins come around 4. Aromatics, amide protons come around 7. Acids and aldehydes come around 11, 12 ppm. So when you look at the spectrum, and if you see peaks somewhere around 10, 11, you know that there are probably acids, aldehyde contain all 6 aldehyde. If you see peak around 7.2, 7.3, and some short doublet peaks, they are all amides or aromatics. And if you the methyls normally come around 1 ppm, quite sharp signal, and there are multiplets around the CH2, CH comes somewhere here. Okay, so that would be the typical proton spectrum range. The same thing continues with the carbon chemical shifts also, because in both chemistry and biology, carbon are also very commonly used. The only thing is the range is quite big here. Normally the proton stops at 10 to 15 ppm, whereas in carbon it goes up to 200 to 250. Now again, the pattern would be the same. Around 10, 20 ppm, it is all the aliphatic CH3, CH2s and all come here. Normally, it is in that range. CH3 comes around 10, 20 ppm, CH2 come around 30, 40 ppm, CHs come around 50 ppm and all. Aromatics and all come at 120 ppm, and carbons comes at 180, 200 ppm. The ketones and all come at 200 ppm and all. So this is the general things. Looking at the spectrum, you can already guess what kinds of groups of things are present in the spectrum. Okay. Now, just before going, I just want to show you one spectrum. This is again, when you record an NMR spectrum, you should have this chemical structure available. Very small molecules, one can deduce the structure from NMR spectrum, but as the size increases, you cannot deduce. You should have this chemical structure. So you should have this is octopeptide. I have written the chemical structure above, and that is the corresponding NMR spectrum. This is reasonably a decent spectrum. Now, if you have such a decent spectrum, sharp resonances, well-dispersed spectrum, then you can analyze further. So if it is not a decent spectrum, you should make it decent by changing the pH or changing the solvent conditions or raising the temperature. Do something so that it gives a decent spectrum. Then only you can analyze. If they are broad spectrum and all, you cannot analyze the spectrum. Now, another important thing here, every proton here, this is a proton spectrum, like every proton here must have a peak here. It could be overlapped and all, but every proton must correspond to a peak here. And conversely, every peak here must correspond to a particular proton there. If there are excess peaks, then there are impurities. You have to go back and purify your sample or give some reason why, like solvent molecules come here. There would be some drop of acetone added because you have not cleaned your NMR tubes. Such things appear. So one has to account for that. Likewise, if there are some peaks missing, then you have to go back and look at your structure. Either your structure is wrong, or if you synthesize, your synthesis is wrong. So there has to be a 1:1 correspondence. Like here, there are 8 NH protons, all 8 NHs come here. There are 2 aromatic, there are aromatics here. And there are this methyl peaks, there are so many methyls here, they all come here. There are so many other aliphatic, they all come here. So looking at the spectrum, you can say directly this is a peptide spectrum. There are so many NHs, there are so many methyls and all. So normally, as I said, this is the amide region, this is the aromatic region, that would be the water peak. Normally comes around 4.8 ppm. And that is the C alphas in a peptide sequence, and the C beta, C gammas come around here, and the methyls go there. So this is the typical NMR spectrum we come across. Okay, as I was telling you, you should have a clean spectrum. If you don't have a clean spectrum, there is no point continuing the analysis. Now, this is another, we designed peptide. There's relatively big peptide, about 33, 32 residues. And now you see it's a horrible spectrum. So this was soluble only in methanol. It was not soluble in other solvent. When we recorded it, and it's all messed up. Everything, there's too many overlaps here. That's because it doesn't have a decent structure. Now, to improve this, we have to do something, change the solvent or heat it up, because it could be aggregated. No, if it is aggregated, there are too many molecules coming together and form hydrogen bonds and all. Now, if you heat it up, it breaks this hydrogen bonds, intermolecular interactions are removed, then things may improve. Now, there is a very subtle improvement, but not a big improvement if you heat it. Now, then we added some other solvent like DMSO, and then there are again a small improvement there. Now started resolving, but not sufficient. Now again, further, we didn't give our hope. We further heated it up, but instead of improving, it became bad. Now we increase the other solvent, or you can do various things. And if it doesn't improve, we cannot do anything. We can simply reject the spectrum. We cannot analyze the spectrum at all. So one should have a clean spectrum to go ahead with the analysis. So recording 1D spectrum itself will tell you there should be sharp, well-dispersed resonances. If it is not, do something like this or do something else, and then go ahead. Otherwise, you cannot do it all. You have to give it up. Okay. Now, finally, I want to tell you some structure aspects, how structure influences this chemical shift. Now, as I said, every molecule has a unique spectrum. Now, like this is alanine amino acid. Now, if you take alanine amino acids, there are 3 kinds of groups here. There is the CH3, normally comes at 1.39 ppm, and there is the C alpha proton, comes at 4.4 ppm, and there is this NH, which comes at around 8.2 ppm. So, but as I said, alanine is a unique, but it should give only one kind of spectrum. Now there are various proteins stored in the data bank. There are lakhs of proteins stored in the data bank, and these lakh proteins will have a few hundred lakhs of alanine residues present in it. Now, if you map all these alanines, in principle, they should all come at one. The methyl should all come at one position. Alpha should come at one position. The NH should come at one position. But if you see, there is a distribution. There is no one position. There is a distribution of chemical shift. Of course, at one, like methyls, 3.9, there is a spread. Alpha around 4, there is a spread. For methyl, there's a spread around 8 ppm. Now, why they spread? This is because of the secondary structure. The secondary structure or the tertiary structure influences the chemical shift, and one can utilize the perturbed chemical shift to measure or to indicate what are the structures. Normally, if it is a helical secondary structure, they are upfield shifted. They come above the normal value. So the normal value is called the random coil chemical shift. Now, if this alanine were not structured, or they call it the random coil value, it would give, if all of them are unstructured, they will all come at one particular position. Because they are structured, they disturb they perturb the chemical shift, and helices normally perturb it and then come above on the right side of the normal peak. So normally, if you see the peaks here, then you can imply there is a helical structure. Likewise, if it is on the other side, like 5 ppm and all, then it's indication of a beta sheet structure, extended structure. No, I have not defined what is helical and beta structures. Probably you will read it about it, or you already know about it. These are the secondary structures, and they fold into a globular structure from the tertiary structure, which is finally important for their function. So we will eventually go to that level, how to get the secondary structures, how to get the tertiary structures from this NMR. So now here is already some indications what kind of structures are present simply at the chemical shift. Now one can use normally, more useful thing is the C alpha chemical shift, the proton C alpha chemical shift, or the carbon C alpha chemical shift. Others also can give, but the others like NHS have various contributions, so they are not ignored. Mainly the C alphas are showing a decent shift, so they are taken from the C alpha, either proton or the carbon chemical shift. One can get from the betas and the gammas, but the most useful is the C alpha chemical shifts. Okay. Now, there is a person called Vishers and Sykes works in Canada. They are the person who gave this first, how to get secondary structure information from the chemical shift. Now, what they did was they take a protein sequence containing about 50, 60 amino acids as a test case, and then they measure the C alpha chemical shift of all the residues. So there are 55 residues, there are 55 alpha, there are 55 C alpha chemical shifts. Now, when they measured it, now what they did was they did the experiment, measure this experimental alpha, and there is a random coil value. As I said, there is an isolated value. And if you take this random coil value, subtract from the experimental value, or whatever, if it becomes negative, this is called delta delta. So capital delta was small delta. So it's called delta. So this is the difference in chemical shift of the experimental value minus random coil value. If it is negative, simply put a -1 in that position. If it is positive, put a +1 in that position. So if you do that and you draw this graph, now you see that a set of +1s. Now you are sure, because it is all +1, it is low field shifted. Now that stretch is supposed to be containing beta sheet structure. Now if there are a stretch of negative values, then let's say they are helical values. Now simply by looking at the chemical shift values, you can determine the secondary shift, whether it's a helical structure or a beta sheet structure, or somewhere here they are all random coil. There is no structures here. So one can get this information directly from the chemical shift. And now people more extensively use this to get these structures. Eventually, one day, I think it will, all the even tertiary structures are obtained by this chemical shift, but the day long is still far away. Okay, now this is yet another example in our lab when we are designing these helical structures. This is about 26 amino acids residues. This is, we introduce some known amino acids to get a helical structure, design a helical structure. And to make sure it has formed a helices, there are other parameters like NUCLEI and all, but simply looking at the chemical shift, we can directly say it has already formed a helical structure. Now, what I have done here is I should have taken the difference and put -1 here. but I have simply put the exact values, and you see all of them are negative, kind of indicating they formed a helical structure. And so we also have designed a sheet structure. So now this is a 4-stranded beta structure with hairpin turns around. And now you can see the sheets, they are all positive values. You can clearly identify 4 sheets simply from this chemical shift table. There are 4 strands, and whatever this turn is represented here, there are 3 turns and the 4th strand. So straight away, the chemical shift gives you some information on the secondary structures. Okay, going further, so that's about briefly about the chemical shift. We will move on to the next parameter called the spin-spin coupling, represented by J, or it's also called the scalar coupling. The most important thing here is the information is transferred to the covalent linkage. Now, in the NMR spectrum, we normally, as I mentioned, you don't see a single peaks, especially in the proton spectrum. Now, they are either, sometimes you do see a singlet peaks if they are not coupled to anything else, or there will be a doublet, there will be a triplet, there will be a quartet, there will be a pentet, there will be a multiplet, all kinds of things we see. Now, how do these arise? Now, these splittings are caused by interaction between nuclei, which are connected through bonds, mainly covalent. So one has to be careful. It's mainly covalent. I use the word mainly covalent because these days, across hydrogen bond also one sees, let us not go into those details, but let us stick to that. There should be covalent linkage. Now this again has to be maximum of 3 bond away. It could be 1 bond away, 2 bond away, 3 bond away. There could be a covalent linkage, 4 bond, 5 bond away, but you don't see the splitting arising out beyond 3 bonds. There are again rare cases, except those rare cases. Most of the time in proton case, we come across interaction between protons which are 3 bond away. In case of heteronuclear carbon 13 and all, we come across 1 bond away, even 2 bond away. Even in proton case, we do see that, but most of the time you see 3 bond away protons. Now, how do they interact? These interactions split the NMR energy levels and results in observation of multiplets of allowed transition separated by amount of energy related to J, called the spin-spin coupling constant. So now the same line which appears one position, because if it is interacting, now the magnetic field seen by that is kind of disturbed by the neighboring nuclei, and and depending on its plus state or the minus state, it either goes downfield or upfield. So the same peak is split into 2 on either side of the center position. Now, if it is 2 equivalent protons, it splits into a triplet, and you get this ratio 1:2:1. And if there are 4 equivalent protons, it split into a quartet and all. So we will see those details as we go along. Now, before coming to the spin-spin coupling, we should be familiar with what is known as chemical equivalence, magnetic equivalence. And we see this splitting if there is no equivalence. Now, let us see what is chemical equivalence. Now, protons must resonate at the same TPM and have the same chemical shift. Now, here is an example of an aromatic ring with 2 substitutions. Now, there is a symmetry across this XY plane or in this one. Now, X is an O2 here or X is CH3 here. Now, if you see there is a symmetry here, and now this H2, H6 are symmetrically related, they come at the same chemical shift, and then that's why it's called chemically equivalent. Likewise, H3, H6 has the same chemical shift, and yeah, they are called chemically equivalent. So this is the real example here. And now that is about chemical equivalence, and there is also a term called magnetic equivalence. Now here you see this molecule, again there is a symmetry across the fluorine-chlorine bond, and now these 2 protons, the highlighted, yellow highlighted protons are equivalent, and they come at the same chemical shift. Now they not only come at the same chemical shift, they also have a coupling with the fluorine. Now this also couples with the fluorine by the same amount, this also couples with the fluorine with the same amount. Now the protons, both chemically and magnetically equivalent, they have the same relationship with the fluorine atom, then we call it magnetically equivalent. Now, if you look at this right side thing, now there is now symmetry at the center of this molecule. But now again, if you look at this highlighted, yellow highlighted proton, now they are chemically equivalent, but not magnetically equivalent, because the coupling between the proton and the fluorine for this proton is different from this proton and that fluorine. So they are chemically equivalent, but not magnetically equivalent, like on the right side. So how do you define magnetic equivalence? Nuclei having the same resonance frequency in nuclear magnetic resonance spectroscopy, and also identical spin-spin interaction with nuclear neighboring group are magnetically equivalent. The spin-spin interaction between magnetic equivalent does not appear like CS3 groups, though they are all different because they are all identical, come at one position, and thus have no effect on the multiplicity of the respective NMR signal. Magnetically equivalent nuclei are necessarily also chemically equivalent. When there is a magnetic equivalent, it has to be chemically equivalent, but the converse is not true. Chemical equivalence need not be magnetically equivalent. Now, these are terminologies. It's useful if you continue an NMR, but for looking at the splitting, there has to be a non-equivalent. Splitting in NMR caused by this non-equivalence of spin. Now, the nuclei in different environment have different chemical shift. That's what we saw in the just now. Now, if these nuclei are connected through chemical bond, as I said, they are connected through this chemical bond. Now, these two protons are 3 bonds away. Now, then they influence the energy levels of the bonded nuclei. If you consider this position, this energy level of this is influenced by this particular proton. The transition of these energy levels causes the splitting of this resonance. If you consider HA and HB, two things, and if you look at HA, it comes at one particular position. And now this HB influences this position because HB can exist in the up state or the down state. It can be the magnetic field produced by this HB can add to the magnetic field or oppose the magnetic field. And again, now the field seen by this is influenced by this. So instead of one peak now, which adds to this, we go on the one side, which reduces the field, goes on the other side. Now instead of one peak, we see the 2 peaks. Now if this HA influences HB, and the HB is also influenced by HA. So the same way the other proton also gives doublet peak. Because it's 1:1, there are 2 peaks, we call it a doublet. And now, these spins, they are called spin systems. Now they are labeled by this English alphabet. Now, if there are 2 spin systems, A and B, and if they are very far away in the chemical shift, they are not called A and B, they are called A and X, like English alphabets, the A and X are far away. So if they are chemically very well separated out, then they are called AX spin system. And of course, there is this coupling there, normally expressed in Hertz. And even the chemical shift difference for this case is expressed in Hertz. Now, the delta nu, and it is called AX spin system. When it is called AX spin system, when the delta nu is very much larger than this J. So there is a convention again. If the delta nu divided by J is greater than 7, then we call it weakly coupled system represented by AX, the English alphabet A and X. Now, if only they are weakly coupled, then one can analyze. If they are not weakly coupled, it becomes difficult to analyze. And now, because we work with higher magnetic field spectrum, very rarely we come across the other case like AB system. Now what are now we talked of AX spin system when they are well separated. What happens if they are not well separated? If they come very close, like if you record the same spectrum in 60 megahertz or 30 megahertz spectrum, these chemical shifts are very close. Now, when the chemical shift becomes very close, there is an influence on the intensities of the motor mode signal. It's called the roofing effect. The outer signal goes down, and now it becomes difficult to exactly measure the chemical shift values. And now, because they are very close, we call it strongly coupled and represented it by this English alphabet AB. So AB systems are difficult to analyze. And when you measure the delta nu by J, either they are nearly one or less than one. If it is less than one, it becomes even strongly coupled and analysis becomes difficult. The one solution to do that is to go and record at higher magnetic field spectrum. And now these days we use 500, 600, 800 megahertz spectrum. We rarely come across the strongly coupled spin system, which was the earlier case, 1960s, 70s. We had a lot of these strongly coupled systems. And of course, one can use computers and numerical analysis one can do and get still some information. But with higher magnetic fields, this problem is drastically reduced. Now we have to have equally coupled system to go ahead and analyze the spectrum. Now here is a typical example taken from some textbook. Now earlier they used to record in 60 megahertz spectrum. This is actinium spectrum. There is these three kinds of protons here, HA, HB, HC, because they all resonate at a very close range, and the couplings influence them, and then it's difficult to analyze. Now, the best thing is to take it to higher magnetic field. If you take it to 100 megahertz spectrum, there is a small improvement, but if you take it to 220 megahertz spectrum, there's a drastic improvement. Now, this ABC spin system becomes the AMX spin system, and then it becomes easy to analyze. If you take it to 500 megahertz spectrum, it even becomes simpler. But one can still do this analysis. People did analysis with this spectrum also, but it gets very involved. Now, when you look at the coupling pattern, you see that again for spin-half system, especially the proton spin-half system, and then there are either doublets, triplets with defined intensities. And now they explain what is known as this Pascal triangle. So if there is like a spin system or A2 spin system, there is only one peak. And if it is coupled to another proton, there will be two peaks, which equal intensity. We can call it 1:1. If there are two equivalent protons coupled to A, then it becomes a triplet with intensity ratio 1:2:1. And if it is three coupled proton, the intensity ratio becomes 1:3:3:1, look like a quadrat, and so on and so forth. And now it looks like a triangle here. This is called the Pascal's triangle rule. Now, when you draw this triangle, the coefficients is represented as the coefficients of the binomial expansion equation. And now, I don't know why I'm saying this, but this is again the textbook material. The splitting follow that pattern. Now the doublet is 1:1, whereas the triplet, you add these two, you get the center point and put one on either side. Now, if you go to the triplet, you put one on either side and add these to 1 + 2 is 3, 2 + 1 is 3, and then 1. And if you can keep on building this, 1 + 3 is 4, 3 + 3 is 6, 3 + 1 is 4, and then 1. So then this is how the splitting pattern looks like. The intensity pattern are governed by this Pascal's rule. Now, this is again the typical spectrum. Again, alcohol. Now, as I said, the methyl comes at the highest position. Now, this methyl is coupled to these two equivalent protons, the methylene proton, and it has 1:2:1 ratio. How does this arise? Because these two equivalent methyl protons can be both down or both up, or one up, one down, and there are two possibilities. So that is why you get 1:2:1 ratio. And when you look at the methylene proton, which comes at 3.3, now this split into a quadrat 1:3:3:4. That is because these three protons can be arranged all three down, all three up, two down, one up, two down, and all. And there are three possibilities like that. And that is how you get 1:3:3:1 ratio. And now, as I said, these splittings arise because of this coupling. Now, if there are two spin systems and there are two different chemical shifts, now this is one chemical shift and this is the other chemical shift, there is no coupling, it would appear as two singlets. Now, because of this interaction, because they are coupled by through chemical bond, information from one proton is transferred to its surrounding electron, and this electron information transferred to the neighboring electron, and that influences the base spin system. So information goes through this electron cloud. And now that changes, perturbs the energy levels, and there is no two equivalent levels, they are all perturbed, and there are 4 levels, and that's how you get 4 peaks, and it's a doublet of a doublet. So also, it can be either, the coupling value can be either greater than 0 or less than 0, can be positive or can be negative, and the NMR cannot detect that. You have to do special experiments to get the sign of the coupling. This is called the coupling constant. You can get a magnitude of the coupling constant, but the sign is not straightforward, but one has to do other experiments to get the sign, but that is generally not important. So information is, what is important is this information is transferred through bonding electrons, and this J coupling, unlike chemical shift, is independent of the magnetic field. Whichever magnetic field you record, this value remains same, and normally they are expressed in hertz, generally expressed in hertz. 3 hertz, 7 hertz, 8 hertz, and all. Now, this J value has a very important bearing on the dihedral angles. Especially, as I said, the protein structures are all expressed in, in terms of dihedral angles, mainly phi and psi. Now, this is the peptide chain made of planes. The rotation about these planes is called the dihedral angles. And now there is a chain of nitrogen, C alpha, CO, nitrogen, C alpha, CO repeating. This is called the backbone, and this plane keeps on repeating. Now the rotation about this NC called the phi angle, and the C alpha C prime is called the psi angle. So the whole protein structure is simply defined by these phi psi. Now, if you see this phi angle, now there is this NH and this C alpha 3 bond away. Now they are influenced, each influences the other present. So this NH peak is not a singlet, it's a doublet because of this C alpha coupling. So also the C alpha is split into 2 because of this nitrogenamide coupling. But the C alpha is also further coupled by C beta. Now, this is the C alpha. It's also further coupled by C beta. But whereas NH, there is only one coupling. So one can measure this NH coupling, NHC alpha coupling directly by these amide resonances. I'll probably show you in the next slide. So now that coupling has a direct bearing on the psi value. Now, the Karplus is the person who recorded hundreds of molecules of NMR spectrum and measured these coupling values. And he saw a correlation between the coupling and this dihedral angle. And it lies into, especially in case of protein structures, and this can be fit into a cosine function. And now these coupling values on the other side, and then the theta and the psi are related. And once you get these theta values, one can get the psi values. So directly, simply by measuring the coupling values, you get information on the dihedral angle, a very important parameter. So couplings, from couplings, one can get the dihedral. There are so many other useful information, but from the structure point of view, there's a direct bearing on the dihedral angles. That's the information we get. And now, again, correlating it to the secondary structures. Now, here's again a cartoon diagram I have shown you. Now, if there are these coupling values between the NHC alphas, if it is high, 8 to 10 hertz, normally they would be in the beta sheet structures. So psi comes around 130, 140 degrees. Whereas if it is a helical structure, the values would be low, about 2 hertz, 3 hertz, then the psi would be minus 60 degrees. Actually, as I said, I have simply pulled out this NH region of the NMR spectrum. I've not shown you the full spectrum, only the NS region of some octapeptide. And you can directly measure the separation between these two and expressed in hertz. If it happens to be 8 hertz, 10 hertz, Now, all of them are 8 or 10 hertz, then you say that they all lie in a beta sheet region. If all of them are in 2 hertz or 3 hertz, then they are in a helical region. One can directly estimate that. So also, as I said, chemical shifts are also influenced by the secondary structures. And now, if the chemical shifts are all in the beta sheet region, they will be very well dispersed, both C alphas and NHS like here, whereas in the helical sheets, they are all compressed upfield shifted. So both chemical shift and the couplings has influence on the secondary structure. So that is about the couplings level. Let us move on to the third parameter called the relaxation rates. Now, what are these relaxation rates? There are, as I said, two kinds of relaxation rates. One is called the longitudinal relaxation rates, and the other is called the transverse relaxation rate. Now, what is this longitudinal relaxation rate? Now, at equilibrium, now when you put your samples in external magnetic field, then there is a net magnetization in the z direction. So that's what we learned in the last class. Now all the magnetization in the z direction, there is no magnetization in the xy, so they are all zero. Now, when you pump energy by the RF radiations, if you continuously pump, and now this goes down and then in the z direction gets converted to the xy plane. And because you continuously pump, the population difference goes to zero and there is no more transition happening and there is no magnetization in the x direction. They are all in the xy direction. So there's nothing in the z direction. And now if you stop pumping this radiation, and then once you stop pumping, now it goes to the equilibrium. Now it builds up in the z direction. The magnetization builds up in the z direction. The rate at which it builds up in the z direction is known as the longitudinal relaxation rate. At what rate it builds up is given by what is known as the longitudinal relaxation rates. Now it normally builds up in the exponential function expressed by this equation, mz is equal to m naught in 1 minus e power tau by t1. Now the time constant which describes how this mz returns to equilibrium value is called the spin lattice relaxation rate, governed by this equation. Now T1 can be defined as the time required to change the Z component of the magnetization by a factor of E. Now this particular point, it would have required by amount of E, and that is known as the T1 value. Now this is important factor because when we want to repeat our experiments, we have to have complete equilibrium. Now complete equilibrium is obtained when you wait for 5 times this T1. So we have to want to repeat this experiment, repeat the number of scans. We have to wait 5 times T1, then only you get the full intensity. So that is why this becomes important. So this is the T1. Now, likewise, what is T2? It is what is known as the transverse relaxation rate or the spin-spin relaxation rates. Now, immediately when you apply the pulse or 90-degree pulse, it flips into the XY plane. And once it flips into the XY plane, you remove the pulse. Now they start evolving. There are so many other spins present. They interact energies between them, then they shrink in the XY plane itself. The amount it shrinks in the XY plane is again governed by another exponential function. And the rate at which it reduces in the XY plane is called the T2. Now, this T2 has a direct bearing on the line width, and if it is relaxes very fast, the line width would be very large. If it relaxes to solution, normally they have a decent relaxation rate, we get sharp peaks. Whereas in solids, it relaxes very fast, you see very broad lines. So, so both have important factor on the NMR resonances, and these two parameters are very useful in case when we study dynamics. So for our current study, we won't dwell too much on these relaxation parameters. And one important thing to remember is T2 is always less than T2 at the most equivalent to T1. Now it relaxes first in the XY plane and builds up in this direction. So the one important factor to consider is T2 is always less than or the most equivalent to T1. Now, there are two factors contributing to T2. Normally, it is the pure T2 inherent because of the spin-spin interaction. And if you have an inhomogeneous field, it also contributes to this line. So one has to be careful when you measure this T2. Now, this is the final important graph. Now, when you consider small molecules, normally the T2 would be larger. As the molecular size increases, it depends on the tau c. When you consider size, it's always compared to tau c. What is tau c? It is the correlation time. These molecules all the time tumble around its own axis. Now, the small molecules tumble faster, and the T1s are larger there. As the size increases, now the tumbling rate reduces, and now the more spins, the dipoles interact with each other, which reduces this T1 rate. As the tumbling rate increases, it goes to a minimum, and the T1 increases again. Whereas the T2 this continuously decreases as we go to a higher molecular weight. As you go to the protein level, it becomes more and more difficult to analyze the proton spectrum because the T2 is very short and the lines are very broad. So, hence, one has to remember these T1, T2 values when you record your NMR spectrum. So there are methods to overcome this, and then they are more involved. So when we go to higher and higher analysis, we should consider these factors. Now, the one important on the structure values are, now if there are very tight structure, now the T1 values will be short. Now again, with respect to every residue, there is a T2 value can be measured. And with respect to every residues, if it is a bound structure, all these residues will have low values. And whereas at the terminal, they are very flexible, there are large T2 values. Now, simply by measuring these T2 values, one can get whether it's a rigid structure. Sometimes somewhere in the loop, there is a loop at the center, very flexible, and then you see the T2 value shoots up there. Now you can distinguish which region is bound or tight structure, which region is loose structure. In this particular case, the terminals are loose structure, whereas the central region is a very tight structure. So also the T2 influence, now when you come to the T1, one can measure this T1 and T2 by doing various experiments called the inversion recovery experiments and all. We will not go into those details. And now suddenly you see some changes in these T2 values, and that can establish looking at this particular T2 values, which is influencing the which other resonances and which is contributing to these T2 values. So these are more details. Let us not go into the details. So we will stop relaxation rates at that particular point. Now go to the final factor called the NOE. There is the most important factor. NOE is defined as the change in intensity of one resonance when the transition of the other resonance is perturbed. This is a very useful information. So let us delve sometime on this parameter. Now, this is the normal NMR spectrum. And now, if you irradiate continuously, one can selectively irradiate one particular resonance and saturate that. Now, if you saturate that particular proton selectively at that particular frequency, and now, because of this, the populations get disturbed, and that influences on the neighboring. Now, this neighboring need not be covalently linked. It can be spatially linked. So that is the advantage of this. As I said, in protein structures, they fold around. As I said, the first residue can be very close to the 150th residue, or the 7th residue can be close to the 56th residue. When they come, they get perturbed because of this transition. So you get through space information. Now, the intensity is normally, if it is small molecules, the perturbed intensity will be increased, whereas in case of protein, the perturbed intensity would be reduced. So that we will come to that later, but there is certainly a change in intensity because of this perturbation, and that is known as the nuclear or Hauser effect. Because of perturbation of one particular nuclei, the intensities of the close by nuclei disturb. Now, it's fundamentally different from the rest of the methods. It doesn't depend on the scalar coupling or the through bond coupling, rather depends on the dipolar coupling, what is known as the through space coupling. It has a direct magnetic interaction, so you get the distance information, very useful parameter for structure analysis of NMR. So now this is the typical spectrum we record. Now, if you consider a spectrum, consider I and S spin. Now, if you irradiate S spin and see the perturbation of intensity I spin. Now, this intensity of the I spin represented by eta, intensity of the I spin. So whatever is saturated, the saturated spin is represented by the flower bracket. So if you saturate S, there is an influence on the I spin. Now, how to estimate this change in intensity? They are normally given by the I is the perturbed intensity, disturbed intensity, the enhanced intensity minus the original intensity divided by the original intensity. If you multiply 100, you get the percentage of enhancement. Normally, in case of protons, you get a few percentages. Ideal percentage is about 50%, but normally, practically, you see about 10%, 20% enhancement. Because this enhancement is low, what we do when we record this NOE spectrum, because it's usually difficult to see the changes of the 5% intensity and all, we take a different spectrum. We record a normal spectrum and we record a perturbed spectrum and take the difference. Now, this is the different spectrum. When you irradiate at this particular peak, and now take the different spectrum and increase the scale of plotting. Now you see the irradiated spectrum becomes negative because this is irradiated, this is 0 minus this particular intensity, and multiplied by some 20 times, 30 times, it gives huge one. And now there is other protons are not disturbed, they all go to 0. Wherever it is disturbed, there is a change in intensity, only that peak comes up. So now if you irradiate this, there is a change in the different spectrum. Likewise, if you irradiate this particular proton, now you see there are some other place the change in intensity. So you can map all these irradiating one by one and note down this change in intensities. Now this intensity is a factor of distance. One can convert into distance because this NOE intensity is proportional to 1 over r power 6. And of course, it also depends on tau c. So we'll come to tau c later. And now if you look at this, because this is r power 6, is a very sensitive parameter. It goes to 0 very fast. So if there are these distances, these two protons which are perturbed or within 5 angstrom distance, we can measure that. Looking at the intensities, we can convert it into distances and estimate these distances. So that is how you get the distance information and eventually we can get the structure. Now coming to the tau c, and the NOE is also a function of tau c. As the size increases, now for small molecules, it's always a positive intensity. For big molecules, it gives negative intensity. And in between molecules like peptides and all 1,000, 2,000 molecules, NOE has no effect. So in such cases, NOE has no contribution, but there are ways and means to overcome this difficult region, and we will see that as we go along. So now the most important thing is it provides information on internuclear distances. So it's distance dependence and simply useful parameter. Now this is a graph showing how the intensity varies according to the tau c or the size of the molecule. It's actually not tau c, it's omega tau c. It depends on the omega tau c. Because we record on a particular spectrometer, we can ignore omega. But if you want to overcome that, you have to consider this. So the one thing is, if there's a small molecule like 200, 300 molecular weight, you get positive NOEs. And if it is a 1,000, 2,000 molecular weight, like 8, 10 residues peptides, So omega tau c becomes 0, omega tau c becomes 1, and it has no information. The intensities are change in intensities are so small, we cannot do. Somehow we cannot utilize this data. Whereas when you consider a macromolecule, the change is quite dramatic. There is almost 100% change in intensity, but in the other side, negative intensity. But with a positive or negative, we are considered about the magnitude of intensity, and hence for protein structures, this is a very useful parameter. We can get hundreds of NOEs for a given protein and then convert into distances, and we get so many distance information. And along with distance information, dihedral angle, hydrogen bonds, we get a lot of information. Eventually, we can use this information to build the structure. So the NOE is a very important parameter for protein structures because you get hundreds of distances from these NOE measurements. Now, how to overcome and this tau c? Now, before going to how to overcome that, we all the time think of that there is only one correlation function, but there are molecules which have two different correlation terms. Now, when we were doing in 1984 or so, we saw either we should get either positive NOEs or negative NOEs, depending on the size of the molecule. In a particular molecule, we saw both when you take the difference, we get both negative NOEs as well as positive NOEs. How it is possible? So then that's why we were curious, and then we came to know there are two different correlation times here. Now this is the whole, as a whole molecule tumbles slowly, and that's how they give negative NOEs. Whereas when you consider this tryptophan, this is automatically hanging out. Now this rotates at a much faster speed. There's a different correlation time because this is tumbling much faster, rotating much faster. We see positive NOE. So in this is a specific case or a particular case, we see simultaneously both positive and negative NOEs. And especially these NOEs were very important when we look at the carbon-13 or the N15 spectrum, because of this hydrogen, we can irradiate all hydrogen when we are looking at the spectrum. Normally, when we record the carbon-13 spectrum, we decouple all hydrogen, or we irradiate all hydrogen. Because we irradiate all hydrogen, and these carbons are close by hydrogen, so they enhance the intensity. Now the enhancement in intensity is twice, 2 times, because it depends on the gamma ratios, whereas an enhancement in intensities of the N15s are 5 times. Of course, the gammas are negative, there's a negative intensity enhancement here. But again, for small molecules, these enhancements are very useful, but when we go to the protein, the enhancements are reduced. So this is not useful when we go to the higher magnetic field, higher molecular side. Whereas in chemistry, where we work with small molecules, these are very useful. When we record a carbon-13 spectrum, most of the time we record with proton decoupling, and you see the enhancement here. So now we look at the carbon-13. When we record a carbon-13 signal, we look at how it is influenced by these NOE enhancement. Now, the carbon-13 spectrum, the 1 day of the carbon-13 spectrum, we recorded proton 90-degree pulse and then get. Now, this is how a particular molecule gives rise to. They are quite noisy. But when we decouple the protons, now switch on the decoupler on the proton, irradiate all protons before sending this 90-degree pulse, then you see the enhancement in these carbon-13 signals. Now, these carbon-13 signals are doubled if you use this sequence because of this NOE effect. Because of this NOE, they are all doubled because there is splittings. You see it is not a clean spectrum yet. But now you can do the other way. No, don't do decouple, but decouple during acquisition. If you do decoupling during acquisition, because of this, the couplings are all gone, become singlet, the intensities are enhanced. But there is no NOE here. But if you throw out decouple, there is NOE plus decoupling. You see the quite drastic change in this enhancement. So the NOE is clearly contributing from here. You see how it comes. So most of the carbon-13 spectrum are on here. So I'll take a couple of more minutes and then wind up this thing. Now, not only NOE, one can increase this enhancement by what is known as polarization transfer. Now, can I take a few more minutes?
Yes, sir.
Okay, yeah. The chemists work with milligram quantities, whereas the biologists work with microgram quantities. Again, as I said, sensitivity is a big factor. and now how to improve the sensitivity. So the methods of going to high magnetic field or cryoprobe, which are very expensive, difficult to handle. So what we do is we do what is known as a polarization transfer. Now we have the protons present in many of these systems. Now they are rich in magnetic field or magnetic moment. You can transfer their magnetic moment to the low abundant carbon-13s because the magnetic moment of the carbon times is 4 times lower. So you take the magnetization from the proton and transfer to the carbon-13. And now these pulse sequences help in that. How it does that is a matter of another class. We will not go into those details. If you do the gymnastics with these pulses, it essentially brought these two energy levels equivalent, and then you can transfer, and then you see the dramatic increase in this polarization. And the carbon-13 signals, they are 4 times enhanced. The only condition is they have to be coupled to the protons. So this is the normal spectrum, and this is the enhanced spectrum. Only thing is the non-protonated carbons doesn't come here. And the one more important thing is the final pulse can be tuned to various angles. It can be in a normally 90-degree pulse. If it is 90-degree pulse, it gives one kind of spectrum. It is 45-degree pulse, gives another kind of spectrum. It is 135 degrees, another spectrum. So you can edit your spectrum, which I show you in the next spectrum. So by changing this 90 degrees, these are called the depth spectrum. We very commonly use this spectrum in the NMR. Now, this is the normal carbon-13 spectrum. If you use a 45-degree pulse, now you see the normal NMR spectrum except this non-protonated spectrum. So you can easily identify which are this non-protonated spectrum. And now if you put a 90-degree pulse, and now if you see the various CHS and CH2, CH3s, the dependence are different. Now the CHS vary as the sine theta, whereas CH2 varies as 2 sine theta cos theta, whereas CH3 varies differently. Now at 45 degrees, they all provide some intensity. So you put at 45 degrees spectrum, you get depth 45 degrees. This is 45 degrees, you get this normal NMR spectrum. And if you put at 90 degrees, it picks up only the CHS, whereas CH3 and CH2s at 90 degrees, it's only the CH which has some intensity, whereas CH2, CH3 goes to 0. So you can simply pull out all CHS in the spectrum. Whereas if you put 135 degrees, the CH2 becomes negative, whereas CH3 becomes positive. So you can distinguish between CH, the odd number of protons and the even number of protons. The CH2 becomes all negative, whereas the CH and CH3 becomes all positive. Now, by combination of this spectrum, you can pull out only CH3s, only CH2s, only non-protonated carbons and all. And we take a practical example. This is an example of terpenoid. Now, to analyze the spectrum, now we can pull out non-protonated carbon, and you can pull out CH2s and distinguish CH3s, only CH2s. And then, no, I have not discussed the 2D spectrum. Now, once you have identified carbon, you can map onto the proton. We will tell you tomorrow what are the 2D spectrums and all. And you can analyze the spectrum. Now, this is the blow-up region of the spectrum. If you know carbons, you know the proton. You can transfer these assignments there, and one can get more information about what is known as multiple bond coupling. So these are the more details. We'll discuss it tomorrow. And one can do the NOE experiment. And this is the 2D version of this. We will come to that tomorrow. And you can get the stereochemistry, which proton comes near which proton. And you can get those information from them. And one can do 1D NOEs also. You radiate peak by peak and see where intensity is that. And eventually, you can get this structure. You can tabulate the chemical shift, proton chemical shift, and carbon chemical shift, the multiplicity factors, and the stereochemistry of all that. So with that, I think we will stop today's lecture. And tomorrow I'll go and discuss about this 2D NMR and try to give some more examples. And sorry, I've overshoot today's, and I'll stop it for the day. So if you have some questions, if we have time, we can discuss. Okay. I'll stop here.
Thank you very much, sir. Students, I would like to request you, if you have any questions, please do ask the questions for today. Do you have any questions? Okay, as sir has explained very nicely, I think the whole of the concept of NMR would be quite clear in your mind by now. And so we can just go, sir can go ahead through the application of this NMR on peptides and all that things. I hope you will just read through all these things. YouTube link is available to you, so you can just rewind the YouTube link, and you can go ahead with these these 2 days lectures for how many times you like, and then you can go through the books also, which have been recommended by sir yesterday, and some of the books which are there in the department, and some of the books, ebooks too, which we have referred to you through Enlist and InflibNet. So you can open library through remote access. You can access these books, and you should be ready by questions, and you should be ready by the applicatory part when sir will tell something about the applications of NMR for peptides. And then tomorrow we'll be moving with the last part of this lecture series. And I would like to thank Dr. Ragothama for today's lecture. We were having principal sir with us also for some time, so I thank him also. He was here because of some administrative work. I think he might have left. Yes, tomorrow we'll be having head of the department, Dr. Brijesh Pare, as well as the principal of the college with us. So tomorrow we'll be moving ahead with all those things. So thank you very much for today. Thank you very much for being with us. Thank you, Dr. Ragothama. Thank you, participants, for being with us. Thank you very much.
Thank you, ma'am. Okay.
Thank you, sir. Thank you for being
with the session now.
Okay, thanks.